So we have this formula that E cell is equal to E of the reduction for a cathode minus E reduction for the anode. And even though the anode is where oxidation occurs, if we look at the reduction direction of it, that gives us the negative of what the oxidation would be. So that's why there's a minus sign here. So let's just look at an example. And 2 plus. So I'm just going to write out the net ionic equation here. Going to chromium. Chromium goes to a 3 plus. And these would be aqueous. And then we got tin. Solid. Okay. So if we want to know what the voltage would be if this was a cell where the chromium and the tin would be separated, we can calculate that by looking at the table of reduction potentials. So this would be the cathode. This would be the anode. Okay, now the cathode reaction up here is in this direction, but the anode reaction is the reverse of this. But this is what would be in the table. So these would both be for the reductions. So you take the minus 0.14 volts, and you subtract from that a negative 0.73 volts. A positive 0.59 volts. For a cell to be spontaneous, to be a voltaic cell, the direction of the reaction has to be such that you come out with a positive E0 for the cell, a positive voltage. If this would have come out with a negative voltage, that means we would have had the reaction wrong. It would have been turned around. And then we're not talking about a voltaic cell. We would be talking about an electrolytic cell in that case. So the E cell being positive is for spontaneous. That's a takeaway. But how does that relate to the other energies that we had talked about in the previous chapter in the thermodynamics? Well, the relationship is the following. The Gibbs free energy change delta G really defines voltage with the following relationship, that it's equal to minus N, capital F, times the E of the cell. Okay, delta G is equal to minus NFE, where N here are the moles of electrons. And this would be per mole of reactions. This would be the moles of electrons transferred in a mole of reaction. The F here is Faraday's constant. So that's just a number, 96,485. And that has units of coulombs per mole of electrons. Okay, so you have moles of electrons times coulombs per mole. So the combination of N and F is the charge that's passing through a wire in a voltaic cell. This combination, it represents the charge. And remember that E is voltage, and it's an energy per charge. So when you take joules per coulomb, joules per charge, that's joules per coulomb, and multiply it by the charge in coulombs, then the units you have all together here are the same as delta G. They're both units of energy. Okay, so they both be in joules. So that's what relates these two together. But very important is that there's a negative sign here, spontaneous reactions. So now we have three things that we can say indicates something spontaneous. If you have a entropy of the universe increasing, if you have free energy change being negative, and now if you have a voltage, potential for the cell being positive. Any one of those are indicating a spontaneous reaction. So non-standard conditions would be when concentrations are not 1 molar or when pressures are not 1 atmosphere. In other words, T ln of Q, where Q is the thermodynamic reaction coefficient, and it's got the products over reactants just like the equilibrium constant does, but these are at whatever conditions you start with. These are initial conditions. Okay, so we worked with that formula in the last chapter. R here is the gas law constant, 8.314. T is the temperature in Kelvin. Standard delta G and the standard potential. We have the non-standard delta G and the non-standard cell potential, and then keep the rest of it the same. We have these negative signs. We can get rid of the negative signs by dividing both sides by minus NF. So if we had these in there, but we divided by minus NF, that means this would also get divided by minus NF. And so we end up with another formula, but this time it's non-standard for cell potential. This is called the Nerst equation. So this side would just be the E, because all this stuff cancels out. This side would just be E0 right here, because this cancels out. This would have a minus sign, so it'd be minus this expression. And then you still have the natural log of Q. Okay, so that's the Nerst equation. You use it in a very similar way to the delta G equation, which means, name of it, you got to calculate that quantity. Except now to calculate Q, we have to have a balanced equation with the chromium and the tin. Okay, so that's our unbalanced equation. I'm going to balance it by doing half reactions. I could just balance the charge, but I think it's easier to see where the electrons come in when I do the half reactions. So let's write these half reactions here. So we have the oxidation half reaction. Chromium goes to Cr3 plus 3 electrons. And then we have the reduction, N2 plus 2 electrons goes to tin. To balance it, the number of electrons on both sides have to cancel out, which means taking this and multiplying it by 2. Taking this and multiplying it by 3. So when you do that, on this first equation, you're going to have 6 electrons on the right, and the second equation, the 3 times the 2, is going to give you 6 electrons on the left. So what you get out of this is the fact that 6 electrons will end up being transferred in the balanced chemical equation, which means that N equals 6. The N in that Nerst equation equals 6. But let's bring this down and show the balanced equation, because we also have to have coefficients in order to get Q. Okay, so we add all this up, we get 2 chromiums plus 3, 2 plus the aqueous goes to 2 chromium cations. That's 310. Okay, so that's the balance equation. I'm going to answer this question. What is equals 1 molar and concentration of chromium let's say 0.1 molar. Okay, so that's non-standard condition because of the chromium. This would be the same as standard condition. And in this first part, I'm just asking for Q, but I'm going to add another question here. We set that up as a cell. What would be the potential? Okay, so the Q, remember, you don't need the solids in there. It's just the aqueous solutions. The chromium on this side is a solid, and the tin over there is a solid. Those aren't going to appear, which means the Q is going to be the concentration of that product, chromium, to that power, because the coefficient is 2 here for the chromium, so it's going to be squared divided by concentration of the tin plus, and that concentration would be Q. So this is products over reactants initially. So we put in our information from the question here. The top number here is going to be 0.1 molar squared. The bottom number is just 1, which is Q. So that's going to be 0.1 squared, which is going to be equal to 0.01. Let's say, and that's unitless. Okay. Now we have everything we need to know to calculate E. We can use that value that we did in the standard example, where we came out with 0.59 for the E0. So we'll use the Nerst equation with that. So E equals E0 minus RT over NF, natural log of Q, which in this case is 0.59 volts. I remember where that came from. Minus, move over here, 0.314 joules per mole Kelvin. You're going to be at 25 degrees centigrade, because you do need that temperature in the formula. So that means this would be 298 Kelvin. And then that's over N, which we said was 6. And the F is 96,000. And then, okay, and then we have ln of 0.010. Just the natural log part is a negative number, is minus 4.61. And then you multiply all this stuff by it. It's minus 0.0197, which is about 0.02. So our E then is going to be 0.59 volts minus a negative 0.02 volts. And then the final answer, minus a negative is plus. The final answer is 0.61 volts. So 0.61 volts is a non-standard potential for that reaction. Notice no products, that's where we have the largest cell potential we can have for any particular system. All reactants and virtually no products. And as the battery runs down, that means you're building up more and more products of whatever that reaction is in the battery, until you reach a point where you're so close to equilibrium that the voltage is essentially gone down to 0 or near 0 for that cell. So the voltages change as the reaction proceeds, and the concentrations change. And you can see that because of the Nerst equation. It's right here in this cube.